Okay, chapter 13 is going to take us through our different types of renewable energy. We're going to start with solar power. We'll talk about two different ways, passive and active. Then we'll hit on biomass, which is mass of living things, so things like wood and corn and ethanol. We'll move to wind and water, and then we'll end with geothermal. So those are our primary types of renewable energy we'll hit on in chapter 13. Now, before we start our energy sources, I do want to talk about ways we can conserve energy. So we've already talked about one way, and that's in transportation, making our miles per gallon more efficient or switching to things like hybrid. So the best thing we can do for our future of energy is find ways to conserve what we're already using. And one of the big ways that we can do that on a small scale is by taking a look at our houses. One thing in our climate is we definitely need insulation. You need to have the appropriate insulation for both warm and cool weather for our climate. And also the lower the temperature, the thicker the insulation that you'll need. Now, one big way that we lose energy is through leaks in our windows. A lot of you guys might have double or triple pane windows, and when you do that, when you have 2 or even 3 panes of glass, you will have a gas in between those panes, and that gas will help to slow down the loss of heat and energy. Now, another big energy sink is water heating. A lot of you probably have a very large water heater in your utility room. And what that does is it keeps hot water all the time, regardless of whether or not you currently need it. So even if no one's in your home right now and nobody needs hot water, you have it ready to go. So we do have the technology, something that's called a tankless water heater. And this is a box on your wall that has a pipe running through it, and water will be heated on demand. So those of you with large families who get stuck with a cold shower, this could be a solution for you. In our kilowatt lab, hopefully you were as surprised as I was by how much we've improved the efficiency of our light bulbs. That incandescent or the filament light bulb was incredibly wasteful, and all that waste energy is turned into heat, which is not what we want a light bulb for. So by improving our lighting, that alone can save a lot of energy by switching to LED or compact fluorescent light bulbs. Another way to improve our efficiency with lighting is actually to use passive solar energy. We're going to be talking about this in just a second, but using just light energy from the sun, the way you place your windows, maybe a skylight, that can definitely improve your efficiency and save you some energy. And then finally, taking a look at our appliances. Most of you guys, if you have any relatively new appliance, it's probably what we call Energy Star. And so that means it has the most up-to-date technology that's conserving energy. So by just making some small changes, that's a big step that each individual can make to help the future of our energy. Now, the ways that we encourage this to happen, really it's economics. You have to hit people in their pocketbook. So it's really cost of things that are going to drive people to change their behaviors and maybe switch to alternative fuel sources. Now, 2 primary ways that this is done is through subsidies and tax breaks. Now, these are both economic incentives that we can use, but they are just framed a little bit differently, in that subsidies are government funds that reduce the purchase price for consumers. So this is like the government is giving you a coupon to make it more affordable to buy. Now, this is a really important one because otherwise these different types of energy sources just may not be obtainable for a large percent of our population. So it makes things more affordable and maybe will make people to make that choice above something like a fossil fuel. Now, another one is a tax break, and so this is a refund after your purchase. This wouldn't come until you file your taxes. So a lot of times if you buy Energy Star appliances, you will get a tax break for that. But you do have to pay the purchase price up front, and that's not always possible for everyone. Say if you're trying to look at solar panels for your house, those are very expensive. And yes, you might get a tax break at the end of the year, but in order to be able to pay all that money up front, just not possible for some people. But these are 2 economic ways that we can encourage people to make different energy choices. The key thing is that you need to make things more affordable for the behaviors that you want, say sustainable or renewable energy, and tax those that you don't, such as fossil fuels. Currently, we do the opposite. So our first type of power I want to talk about is solar energy. Now, one of the great things about solar energy is that it's very, very abundant. But one of the big problems is it's just not available everywhere. So Well, I want to talk about two ways that we take a look at solar energy, both passive and active. So what passive solar energy means is we're taking either light or heat from the sun and we are not converting it to electricity. Most of this is done by building design. So if you take a look here, this is an overhang to a house. And what an overhang can do in the summer when the sun angle is high is it can create shade. So this is why you might see a lot of southern houses with big front porches with big overhangs, because that provides shade in the summertime when they get a lot of heat. In the wintertime, when the sun angle is lower and you might want that light or heat, the sun angle can go underneath that overhang and still light or heat your house. The same thing can be done with a deciduous tree. In the summertime, the leaves will provide shade. In the wintertime, when you want that light and heat, the sun will go right through those empty branches. Now, another thing that you can do with your design in a passive solar design is on your floors, you can have thermal absorbing tiles. So what that does is when light hits these tiles, it absorbs the light energy and releases heat, very similar to like what you would see in a greenhouse. Another thing that you might do is have a solar chimney. What this does is just takes advantage of convection. It allows heat to rise and exit out of solar chimneys. So this is a way to cool your house. So you can have different ways to heat and cool your house depending on the season. Another thing that you might want to use all year long are things like skylights or solar tubes. These are just ways to allow sunlight to be able to come in your house, and then you don't have to turn your lights on so much. So those are all some passive solar design. One other one would be maybe sometimes you might see a black bag on a roof. That black bag would contain water. It takes a lot of energy to heat water, so if you can use the sun to at least raise the temperature a bit, then your hot water heater doesn't have to work so hard. Now, active solar power is actually converting the energy of the sun into electricity. This can be done on a large scale like this solar power tower. All of these mirrors in these fields will direct the sunlight to one common spot. So that's concentrating the energy of the sun. And then you'll be able to heat a liquid in this tower. That liquid will be turning into steam. That steam will turn a turbine, and that turbine will be connected to a generator. So this is a large-scale solar thermal plant. Now, on a small scale, you can use photovoltaic cells. So these are our solar cells. You might see these on your calculators. Now, the primary component of photovoltaic cells is silicon. So this is a very common element in our Earth's crust, and I'm going to show you how these photovoltaic cells work.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the P-N junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles, called photons, shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the P-N junction, they'll only go one way. The electron is drawn to the N side, while the hole is drawn to the P side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles, which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
Okay, so one of the big cons they had with solar power is that it's just not available everywhere. And that's true. Here in a map of the United States, you can see our southwestern quadrant. That's going to be the most reliable source of large-scale energy. But it can be done on a small scale for your houses to help offset the cost of your electric bills. So our pros and cons of solar power. The big pro is that we have an unlimited supply. The sun is going to be around for a very long time. And there is no direct air or water pollution. Now, you're going to hear me say this phrase for a lot of our renewable sources of energy. And you're not going to be able to say that, though. You're going to have to be very specific of what air pollution it doesn't create. No SOx, no NOx, no particulate matter, no carbon dioxide from the use of solar power. Now, that's a very important word there, the use of it, because to mine the silicon to construct those solar panels, part of that whole fuel cell cycle for solar cells, that does require fossil fuels. That does create air pollution such as CO2 and particulate matter. But the use of solar power directly does not. Now, some of our disadvantages, like we saw, is not going to be cost effective all the time. You do need to line them up in a series. One big issue with it is that every day nighttime happens. So you do need to have a storage. You do need to have backup, and that typically is in the form of a battery. The construction of the battery, the disposal of the battery, those have environmental implications, that there's a lot of nasty chemicals in batteries that can leak even if it's properly stored in a landfill. So that battery can really be a problem. And it is very site specific. So those are our overall pros and cons, that it is clean, no SO2, no particulate matter, no carbon dioxide. But one of the biggest disadvantages is that site specificity and the battery backup that it requires. Now, next one, we're going to take a look at some of our other forms of renewable energy, and we'll be sure to be doing a graphic organizer of solar panels in class.